Hi, I am Hussein Ahmed Chaudhary. I'll be talking on effective clustering of single-cell RNA-seq data to identify biomarkers without user input. These are the outline of my presentation. First, I'll share what are the main objectives of my PhD work. Then I'll go through thesis contributions. Then I'll be talking on a proposed clustering method, UIPBC. Then I'll share some future work. These are the main objective of my PhD work. First one is to analyze RNA-seq and single-cell RNA-seq critical disease count data using computational biology approaches to identify potential biomarkers. Next one is to address the limitation of state-of-the-art clustering method which are developed or applied on single-cell RNA-seq data to expedite the automation of biomarker identification. Now coming to the thesis contribution, I have performed two literature review, and first one is focusing on each step for generating count data, and next one is about what are the different types of analysis we can perform on RNA-seq count data or single cell RNA-seq count data. Then I was involved in developing a pipeline which can generate count data from raw FASTQ file, and I have also analyzed two neurodegenerative disease data. One is related to schizophrenia and bipolar, and another is related to Parkinson's disease. From the first dataset, we have found that differential activation of the immune system components and pathways may drive the common and unique pathogenesis of BPD and SCZ. And from the next dataset, we have found 11 potential biomarkers. These particular genes are differentially expressed in brain region, in Parkinson's disease sample, and they are also member of a co-express module which also contain causal gene for Parkinson's disease. They are sharing pathways and geoinformation with the already established Parkinson's disease gene, and by looking at all these aspects, we declare them as potential biomarker. Then I developed a pipeline which can be used to perform single-cell RNA-seq data pre-processing. Then I evaluated 20 state-of-the-art clustering method on single-cell RNA-seq count data, and I have found density-based clustering show poor performance, and I have also found that specialized clustering method developed for single-cell RNA-seq show better performance than the method which are developed for other applications. Then I developed three clustering method. First one is a density-based clustering method. Actually, after going through different literature, I have found that single-cell RNA-seq data may also contain arbitrary shaped cluster. So that work I have done, and that particular method was tested on 15 synthetic and real-world dataset, and it is outperforming a recent state-of-the-art density-based clustering method. Then I developed two specialized clustering method named UIPBC and UICPC. These methods are compared with 20 clustering methods on 12 real-world single-cell RNA-seq dataset, and we have observed that UIPBC and UICPC are able to perform consistently well on most of the dataset in terms of NMI purity and ARI, and these methods are found to be the best performer. Now coming to the main part of today's talk, a proposed clustering method, UIPBC. Clustering is one of the very important application in single-cell RNA-seq data to identify cell group and studying cell heterogeneity. But however, before performing clustering, different types of pre-processing are required, like removal of doublets or low-quality cell, removal of unwanted genes, under or overexpressed gene, normalization to correct the biases due to different sequencing depth and different transcript size. Transformation is required to transform the discrete data distribution of single-cell RNA-seq to normalized distribution. And after going through literature, I have found that most clustering methods which are developed for single-cell RNA-seq data require user parameter setting. These are some related work. These are applied on single-cell RNA-seq data. And here TSNE, race ID, Serut, SC3, these are actually developed for single-cell RNA-seq data clustering. This method require user input parameter, except CIDR, all the method require user input parameter, and also most of this method also required external pre-processing of the data. These are some density-based clustering. Here HCLCCB is the only user input free method. Other method require user input free. However, HCLCCB integrate a cluster validity index to get quality clustering results. And all these motivations, here you can see most clustering method require number of cluster as input, and some other require selection of cluster center from a decision graph, and race ID and cell would need number of genes user want to keep for further processing, and density based clustering show very poor performance, except AC, LCCB and CIDR other method require user input. And however, the performance of CIDR, which is specially developed for single cell RNA-seq data, seems to be very low. So all this motivation motivated me to develop a clustering method for single cell RNA-seq data. This is the problem definition just to partition a given single cell RNA-seq data, where the cell, say CI, in a group are highly correlated to each other, but any two cell, say CI and CL from say cluster GI and GJ respectively are not correlated. These are the workflow of the proposed clustering method. It accepts a single cell RNA-seq data as input, then some pre-processing are required, and after pre-processing we will get a pre-processed data. But that pre-processed data may also contain different types of biases due to dropout event and noises, because none of these pre-processing tasks actually deal with those type of biases. So to deal with those type of biases, dimensional reduction is found to be one of the best strategy. So I am here performing principal component analysis to reduce the dimension of the pre-processed data. And after that, here I can directly perform clustering using this strategy, but that particular scenario I am considering as individual scenario, and after analyzing the performance of this method on that scenario, I have found poor performance. So I have created multiple data set here, and each of the data set and cell will be there, and in column principal component will be there. And after that I am performing the clustering process. In the first step of this clustering process is finding neighbor search range K. Here K is that value for which every cell in the data set is referred to by any other cell within their K nearest neighbor. And if we consider K plus 1 nearest neighbor, then no fresh cell are referring by any other cell from their K plus 1 nearest neighbor. After getting that particular K, we are estimating the centrality of each cell. Centrality is that is the weighted average of Pearson correlation from a cell to its K nearest neighbor. And then I am constructing subcluster. Before that, I have sorted the cell based in descending order based on centrality, and then I start the process from the first cell, and first I have identified the K nearest neighbor, and from that I again identify the which is the cell has centrality, and that particular cell I am assigning as the level of all the cell present in the nearest neighbor for which we are trying to assign the label. That process will be repeated for all the cell, but in that process there may be a situation like two cell compete to become a representative of another cell. In that scenario, I am using two rules. One is level updation rule and one is level changing rule. And in that way, we'll just create subclusters. They will be very smaller size cluster. And after that, in the next step, I am merging cell based on core cell sharing. Here, the main idea is that here core cell are those cells which have very high centrality. I mean, the centrality is greater than the median centrality of all the cell. And if two cell like C4 and C8 are sharing some core cell from their K nearest neighbor, then we can think that C4 and C8 must be in the same subcluster. So in that way, I am merging some subcluster, and after that, I am creating a KNN graph. here cell are the nodes and edges are the pairs in correlation, and after creating this subcluster I am extracting local cores. Local cores are that cell in a subgraph for which the centrality is the highest, and I am computing the shortest path between each pair of local core and shortest path between each pair of local core. And in that case, if we find a shortest path that passes through very central region from one local core to another local core, and then we can think, I am assuming that those two local core must be part of a same cluster. In that way, I am just finding the optimal cluster present in the data set, and after getting optimal number of cluster, then I am again constructing another graph G2 for merging subcluster based on similarity, and here I am using agglomerative approach to merge this cluster till finding optimal number of cluster. In that way we get the solution for one dataset, and that process will be repeated for other dataset, and finally I am constructing binary matrix for each of the solution. Binary matrix, in a binary matrix, if two cell is a member of same cluster, then the corresponding value will be 1. In that way binary matrix are created for each solution, and then I am building a consensus to merge all this binary matrix, and finally a hierarchical clustering is applied to get the final solution. These are the dataset I have used to test and verify my method. Here column 2 and 3 are the dimension of the dataset before performing pre-processing, and column 5 and 6 are the dimension of the dataset after performing pre-processing. Here you can see the performance of the 20 clustering method on 12 real-world single-cell RNA-seq datasets. Here SC2UIFDBC are the clustering method which are specially developed for other application. TSNA2UICPC are the method which are specially developed for single-cell RNA-seq data. Here you can see the density-based clustering HCLCCB2UIFDBC are showing very poor performance, and HCLCCB2HPC are showing much better performance than density-based clustering. Even they are showing some of them are showing better performance than some clustering method which are specially developed for single-cell RNA-seq data. But overall, you can see the performance of UIPBC is the best in terms of NMI and ARI, and in terms of purity, UICPC is found to be the best performer method. Then I was talking about individual and consensus scenario. Consensus means I am creating multiple solution and getting clustering solution for each of this data set, and finally through a consensus I am getting the final solution. And after adopting that particular approach, I have found significant improvement in the overall performance of my method. Though I am claiming my method is user input free, but it requires some threshold setting. This LRC, low rate count, and SBG, highly variable change selection, these two thresholds are related to pre-processing only, and SI for main clustering process. Here how I am doing this. First, I fixed SBG at 2000 and SI at 0.75, and I was varying LRC from 1 to 10, and I have found at LRC 6 the method was performing the best. Then I fixed LRC at 6 and keep on varying SBG from 2000 to 5200, and found that at SBG 4300 the method was performing the best. And after setting the LRC at 6 and SBG, and for SI we have found at SI 0.75 the method was performing the best. Here you can see that the performance of the method improved for each consecutive threshold setting. I mean, when we were trying to set the threshold for LRC, then we were set SBG and SI randomly, right? Or SBG was set to 2000 and SI was set to 0.75. In that case, the average performance was little bit poor. Then when we set the best threshold for LRC at 6, and try to compute the best threshold for HBG, then we have found the method was performing much better. And when we set the threshold for LRC and HBG best threshold, then we have found that during computation of SI threshold, the performance was improving its performance further. Then coming to the discussion and conclusion, the most state-of-the-art clustering method generally influenced by user input, and the proposed clustering method is compared with 19 clustering method on 12 single-cell RNA-seq dataset, and we have found that the proposed method is performing best in terms of NMI and ARI. And though the method is user input free, but some threshold setting is required, and those are benchmarked after applying the method on multiple datasets. And we have also seen that the method which are specially developed for single cell RNA-seq data, they are showing poor performance, and we have found the only user input free CIDR which average performance is like 0.47, 0.62 and 0.34 in terms of ARI purity and NMI. And the second best method is found to be UICPC, and which showing performance of 0.62, 0.79 and 0.41 in terms of NMI, purity and ARI. And whereas our method show best average performance in terms of NMI, purity and ARIs as 0.66, 0.75 and 0.49. Thus this method may be a great choice for the user. Now in future, I am planning to analyze the effectiveness of these two proposed clustering method and along with other clustering method, and I am also planning to develop a differential expression analysis method, which will be an individual gene-based analysis method. And I have also planned to identify some potential biomarker based on some topological, functional and integrated analysis. I would like to thank my both supervisor, Professor Dhruva Kumar Bhattacharya and Professor Jugal Kumar Kalita, for their enormous support and guidance during my PhD. Thank you for your attention. If you have any doubt, please contact me in this email ID. Thank you.